Welcome back to class 12. I've finished what's in Borgnacki, and I'm going to give some more examples out of Cengel that I think are related to what's in this chapter. These are types of problems that I think you should be able to do, even though we haven't covered examples like them in Borgnacki. I think that this is sort of like I could ask this kind of question, and I would expect you to be able to work your way through it. So here's one where we have unrestrained expansion of water. So we've had problems similar to this, but not exactly identical to it. So we have a rigid tank that's divided into two equal parts by a partition. And initially on one side of the tank, there's 5 kilograms of water at 200 kilopascals, 200 kilopascals, and 20 degrees Celsius. And the other side is evacuated, which means it's in a perfect vacuum. But it has the same volume as on the other side. The partition is then removed, goes poof, goes away, and the water expands into the entire tank. The water is allowed to exchange heat with its surroundings until the temperature in the tank returns to the initial value of 25 degrees Celsius. When to determine the volume of the tank, the final pressure, and the heat transfer for this process. And some of my reasoning in giving you extra examples with all these types of things is this: I want to make sure you understand that you're responsible to try to think and not memorize. So here's an example where it's entirely capable of doing this problem, even though you haven't seen it. Well, of course you've seen it now, but there'll be other problems like this. So let's draw this thing out. And here's our partition. And here is our water. Here's our vacuum. And this is the partition right here. And so this is sort of like our system. And things that we'll know is our system is 5 kilograms, and that's always going to be true. The T1 is 25 degrees Celsius. The P1 is 200 kilopascals. So if we were going to, the place to start is we could get properties for this, or do the best we can. So let's try to figure out what we know that this is probably liquid right now, but let's look it up. All right, so let's go to table B. Where'd you go? Where did we throw up? Go too fast, right? So I always say 25 degrees. Here you go, 25 degrees. All right, okay, well, see, the pressure is higher right here. Our pressure is at 200 kilopascals, whereas the saturation pressure for 25 degrees Celsius is 3.169. So we're definitely a compressed fluid. One estimation we can make is just go ahead and use the fluid specific volume at that temperature. So here's going to be we'll say that the initial specific volume is approximately equal to the fluid at T equals 25 degrees Celsius. And that's going to be 0.0001003 cubic meters per kilogram. It's a pretty good, because we have one thing, we usually treat water like it's incompressible, and it is for the most part. It doesn't. Its density won't change much with pressure. It's almost entirely because of its temperature. The pressure doesn't really. You can squeeze it as much as you want, and it takes a lot to even get a small amount of volume change. So we can go ahead and say volume 1 is approximately V1 times its mass. So that's going to be 0.001003 times 5, which is 0.005025 doesn't make any sense. How did you do that? 0.001035 times. Yeah, I don't know. How did you manage to do that, man? That's all I can say is I don't know. All right, there you go. And this was cubic meters per kilogram. That's kilograms, so that's meter out there. What is wrong with you? That's a long list of stuff, man. So anyway, and then you could say, well, V2 is going to be equal to 2V1 because it's twice the volume because it's 1/2 of the thing. 0.005015. So 2 times that. And so you get 0.01003, as you would expect to, right? We would just multiply it by 10. And now from that, this is going to be weird of us. We could totally have just done this the other way around, but this is how I did it. So that's right. We get the specific volume of taking volume 2 and dividing it by the mass, which was always going to be the same thing. So 0.01003 cubic meters divided by 5, which should be 0.002006. Duh. I mean, it was a silly exercise, I know. But anyway, well, we were asked to find the volume, right? So we were asked to find this up here. So I don't feel that's the volume of the tank, right? So we just answered that right there. So it's not my fault. But we could have just said, well, it's going to be 2 times this, so we just multiply 2 times that right there. All right, I got it. So anyway, if we go up and look at our tables now, okay, so this is, we have to, we were told that T2 is going to be 25 degrees Celsius again, right? But we have a new specific volume. So we have 2 pieces of state data. Anytime you have 2 pieces of data, you're going to be able to find the rest of the data. Anytime you have 2 parameters of a state, you can find the rest. So let's take a look at 25 degrees. Well, it could be superheated, could be, but there's a good chance it might fall into this range right here. So if we go over to here, you'll see that here's the gas is 43.3593. Well, you know, and we already used this for the vapor, for the fluid. So it's in between these 2 values. So it must be a mix of steam and water together, a vapor, saturated vapor mix. So its pressure has to be this amount. So it's kind of amazing. It just went from 200 kilopascals and it flashed, boom, into steam, and its pressure dropped crazy, right? The pressure on the one side. But of course, it was a vacuum before. So what we can write down is that the Psat is going to be 3.169. But how much steam is it going to be? Well, what we can do is we can find what the quality is going to be by writing both of these things down. Let's write down V. We already have VF written down. We can look at VFG. So the VFG is going to be 43.3583. And we might want to use all of these sig figs. And I might want to rewrite all this down because it comes out like very, very small changes. And so the sig figs would be kind of important into this one. All right. So we'll find what the quality is going to be. So we have 0.002006. And I should write down the equation I'm using. You should be used to it not by now, but I think it would be better. V is equal to VF plus X times VFG. Right? You're used to that by now? Hopefully. 0.002006 is going to be equal to 0.001003 plus X times 43.3583. And I'm going to work this out because I was looking at another book and kind of riffing off of that. Ripping off, one of those. And they were careless with their sig figs. So I don't trust them. 43.3583. And we get a really, 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 really small number, right? That's the number right there for our X. We can't even call it like a percentage, really. It's like 0.003231 or something like that. And I'm going to keep all these sig figs here for the time being. That's a very, very non-quality quality right there. But what we could use this for is coming up with the internal energy. Because we could go back to that next page of the steam tables where we have, no, we don't need the next page, we need this page. Internal energy, right there. We can get the internal energy. Is that right? Yeah. And go 25. So we can see those are the two numbers I want. I want U is equal to 104.86 kilojoules per kilogram. I'm messing everything up. It's my fluid, and my fluid gas difference is 2304.90 kilojoules per kilogram. And we can find out what our current state is here. So we go U is equal to, well, let me write down the equation again. It's the same equation as up here, but maybe that's not clear to everyone. So U is going to be 104.86 plus 2.31328 E minus 5 times 2304.90. And so let's see. We'll do that one first. And 104.86. Boom. So that's 104.913. But still in my calculator. What we want to have is the change. Okay, so that's going to be U2. But U1, by the way, is going to be just this. U1 is equal to 104.86. Because remember, this is our way of like guesstimating. We're going to say it starts out just as this. We could also probably maybe look it up. I wonder if we could. Let's see if our tables go there. We have compressed tables. Table 414. They don't have 200 kilopascals. But we could check something here. Check out right here. Here's our internal energy at 520. So at 500 kilopascals and 20 degrees Celsius, they're saying here is what our internal energy is. Let's go back up to this guy right here and take a look at 20 degrees. Look at that, 83.94. So that to me, I wish I'd written down because I can't remember that number. I'm going to go back again. 83.94. Go to our compressed tables. 83.91. These are really close to each other. So my guess is that we're going to be, it's okay to use the fluid internal energies of the saturated state right here. It's right here. So that so we had 25 degrees. So that's the one we actually want. But I was just using this one because you know, we had one to match it with in the other table. So coming back, I feel pretty comfortable that we can say this is the fluid. So when we go to write out the main thing that we're here for, is the heat transfer. Let's go back to our main equation. I think it's always a good idea to just keep going back to the same equation over and over again and recognizing that we're using it repeatedly. There's no work in this system. We're looking for this heat transfer, and we're looking for it between states 1 and 2. So this right here we can find by taking the mass, total mass of the thing, and changing it from here to here, right? And finding out how much heat had to be added to it. So we had 5. Now here is where we needed our sig figs in a big way, because we're going to take this 104.913, and I still have all the sig figs stuck in my calculator without having dropped any, and subtract out the 104.86. See, there's not a lot of them there. So 104.86 subtracted, multiplied by 5. All right, and so you get Q1, 2 of 0.2666, and these are going to be kilojoules. Is that right? Yep, kilojoules. So let's see, the final pressure. Oh, we didn't write down what the final pressure was. I guess we could have done, this could be it. Final pressure is going to be this. But by the way, for homework, I want you to rewrite that out here at the bottom so I can find it. So if you communicate it, right here is the heat, and right up V2 was the volume. This is the total volume right in there. So I think it's a good question because it's not that much different from what we've previously done. But I think a lot of people who who would struggle if they don't really learn the thing. But I want everyone to learn the concepts and the ability to think your way through a problem and problem solve, and not to memorize. So we do more and more problems like this. Not exactly like this, but that's the point.